All right, welcome back to our calculus videos, talking about related rates, and we're going to do an example. And what we have here, and I've already gone ahead and drawn it, so if you want to, you want to pause and copy that down, you certainly can, or if you just want to follow along. We've got a balloon, a hot air balloon that is going straight up. And we have a station off to the left here, which has a rangefinder. And the rangefinder is actually measuring the angle of the balloon. Um, the rangefinder is 500 feet from the directly under the balloon, the liftoff. So when I drew my diagram, what I like to do is I labeled the base as 500 feet because I know that's not changing. I labeled the angle as theta, and then I also added d theta dt to remind myself that angle is changing. And I wrote a height and I wrote dh dt to remind myself that the height is changing. Because remember, we've talked about before, the only thing that you can just plug in as a value at this point is the 500 because it's not changing, it is a constant. So the question is, how fast is the balloon rising? Which means that what we are trying to find is we are trying to find dh dt. So let's see what we know. Well, we've got a right triangle. Looking at this, we see that, we have a tangent problem. So the tangent of the angle is equal to opposite over hypotenuse, opposite over adjacent, h over 500. And we're in a position now to say, okay, we have everything we need. Let's take some derivatives for rates of change. So we know that the derivative of tangent is secant squared theta. We're taking the derivative with respect to time. Derivative with respect to time. Again, WRT with respect to derivative. That's an I. Which means we're going to have to use the chain rule here. So we've got times the derivative of the angle with respect to time. Divided by 500 is the same as multiplied by 1/500th. And the derivative of h is dh dt with respect to time. Here's what we're trying to find right there, dh dt. So let's solve for dh dt. I'm going to multiply both sides by 500, and I have the rate of change of the height with respect to time is equal to 500 times secant squared of the angle times the rate of change of the angle. And now it is appropriate to plug in my numbers. The rate of change of height with respect to time is 500 secant squared pi over 4 and times 0.14. So I could type this into my calculator. I also know that secant of pi over 4 is root 2. Because secant is 1 over cosine, and cosine of pi over 4 is root 2 over 2. So this is 500 times root 2 squared times 0.14. Well, that means that that's 1,000 times 0.14, which means that the rate of change of the height with respect to time is 140. Now, we're not quite done because we need units. Feet per minute. And our interpretation, and this is an important part of the problem, again, interpretation is that when the angle is pi over 4 radians, the balloon is rising at 140 feet per minute. You need to say when your answer is true, and you need to say what it is, and it needs to include units. Okay. I'll be back with one more example. Thanks for watching.